we learned about representations for context free languages, and they are push down automata and context free grammars. We also proved that they are equivalent representations. Today we are going to see a necessary condition for context free languages, which can be used to prove that certain languages are non-context free. And the topic for today is pumping lemma for context free languages. We can try to understand the lemma by considering a context free language and a grammar in Chomsky normal form for that language. Look at this language, which is not to be a context free language, for which we designed both push down automaton and context free grammar. Here is a context free grammar generating this language, which is not in the Chomsky normal form. Here is an equivalent grammar which is in the Chomsky normal form. You can verify that the RHS of every production, there are two productions for the capital S and one each for X, A and B. In each case, the RHS is either a string of two variables or a single terminal symbol. Now let us look at a leftmost derivation and the corresponding parse tree for a string in this language. This is the grammar in Chomsky normal form that we have seen, and we know that the derivation should start with the start symbol, and this is how you can represent that step in the parse tree. Now suppose you apply this production, you are replacing capital S with capital AX, and in the parse tree it is represented as, now you expanded it with AX. A and X are the symbols on the string that you derived. Now suppose you apply the third production where capital A is getting replaced with small a, and this is how you represent it in the parse tree. I hope you remember what are parse trees. Otherwise, please go back and see the lecture where we discussed about parse trees. Now suppose the next step is applying the production for X, which is replacing capital X with capital SB, and this is how you represent it in the parse tree. And then suppose you apply the second production for capital S to replace capital S with capital AB. So this S will be replaced with capital AB, and here this S is expanded to AB. Now you are applying this production for capital A, so you are getting capital A replaced with a small a. This is how you expand it in the tree. Now you can apply the last production for both of these B's, you will get this, and this is the corresponding representation in the parse tree, and finally here also you will do the same. So this is what we already have seen, and we just wanted to recollect a leftmost derivation and a corresponding parse tree. We know that they represent each other. Now we can see something called cutting and pasting in parse tree. This is the parse tree that we looked at in the previous slide, and what is this generating as a string? It is a square b square, a square b square. It is nothing but the labels of the terminal nodes or leaf nodes, which is called the yield of a parse tree. Now, cutting means, suppose you cut the branches of the root node, and what you do is you paste this part of the tree, and not that. Parse tree is representing a derivation, that means you are expanding from the start, simple like this, and you came to capital S again, and then you are expanding S again in some other way. That means you can try doing this derivation or expansion here itself. So, it is quite intuitive to replace the left and right branches of this S with the left and right branches from this tree, and that is what we are trying to do. So, we are cutting this branch and pasting this branch over there. Similarly, you are doing it here. And why is it meaningful is, you are expanding S using some productions from here, and you are expanding the same as here using some other production. That you can do here itself, no doubt, and that is what we did. And if you look at this tree, the yield is AB, and if you want to look at the corresponding derivation, capital S is expanded to AB. This is the production that you applied, that is a second production for S. Then this capital A is getting replaced with small a, this is the production, this is how you expand. Similarly here. So, I just wanted to tell you that for every parse tree there is a corresponding leftmost derivation. Now, we can try one more cutting and pasting. Here what I am going to do is, I will cut these branches of this S and I will paste the branches from this S, is what I am doing. So, what is the left branch? It should be capital A then small a, that is going to come here. Okay. This is cut and this branch is copied to here. And what is the right branch? This was this single tree rooted at B. I am cutting it away and pasting this right subtree. Okay. And that is exactly what I did. You can verify it offline. And why is it possible is because here you are expanding S in these two ways, and you do that from here is what I am trying to tell you. And here you can verify that the yield or the string generated is A cube followed by B cube, and verify that this part of the tree is remaining unaltered, and I am just cutting the branches from this S and pasting from here, and that is what I did. Okay. So, basically what we observed from this slide is that a tree rooted at a non-terminal capital X, for example capital S here, can be replaced with another tree rooted at X. For example, here we can consider this as cutting the subtree rooted at S with another tree rooted at S itself. So, we are replacing this with the tree rooted at here, and that is what we do here. Okay. And now, look at a parse tree for a Chomsky normal form grammar. You can see that the parse tree is a binary tree. For example, this is the parse tree that we looked at in the previous slide. That is of course a binary tree. And why is it to be a binary tree in general? Because the structure of the Chomsky normal form grammar demands to have maximum of 2 simples in the RHS, and hence for every node there can be a maximum of 2 children, and hence it must be a binary tree. Now, level number of a node in a binary tree is the number of edges to be traversed to reach that node from the root node. For example, level number of the root node is 0 because the number of edges to be traversed to reach that node from the root node is 0 here. Here it is 1 because one edge needs to be traversed. Similarly, you can see. Now, the height of a tree is the highest level number of nodes in it. So, in this case it will be 6. And terminal nodes contain terminal symbols and appear only in the leaf nodes in a parse tree. For example, if you look at these trees and labels, all internal nodes or non-leaf node is having a label which is a capital letter, which is a variable or non-terminal of the grammar. And a leaf node is also known as a terminal node because it contains a terminal label or terminal symbols. These are some basic aspects about trees. Now we can collect some more non-facts about binary trees which are very relevant to have a necessary condition that we are going to discuss, which is pumping lemma. This is a complete binary tree of height 3, and from this illustrative example we can see that the maximum number of nodes at level I from 0, 1, 2, 3 is 2 to the power I. At level 0 it is 1, 2 to the power 0. At level 1 it is 2 to the power 1, 2 nodes. At level 2 it is 4 nodes, and level 3 8 nodes, 2 to the power 3. It is very easy to prove using the principle of mathematical induction, because if there are n nodes in this level, in the next level you can add maximum 2 nodes for every existing node. So, the next node, in the next level the maximum number of nodes will be twice as that of this. So, if this is 2 to the power I, then 2 into 2 to the power I is 2 to the power I plus 1. That is the proof if you want. So, just take it as granted. At level I there are going to be maximum of 2 to the power I nodes. Maybe you are not having some of these nodes, that is why maximum is 2 to the power I. And when a binary tree has a height h, here h is 3, the maximum number of leaf nodes possible is 2 to the power h, which is a result which follows based on this result, because here the maximum level number is h and there should be the maximum number of nodes. By this it is 2 to the power h. For example, here you have 2 to the power 3, which is 8 leaf nodes. And if a leaf is at a level lower than the height, for example, here the height is 3, suppose you have a leaf node that is without a child at a level 2 or less, then it will have less than 2 to the power h leaf nodes, because 2 to the power 3 is 8, now you have only 6 plus 1 7 leaf nodes. It is also very easy to observe. So, the point that you have to take is, if h is the height, then the maximum number of leaf nodes possible is 2 to the power h. When a tree has height h, the maximum length of a path from the root node to the leaf node is also h. For example, here if you take any path, see that there are 3 edges, which is the height of the tree. So, that also is an easy result to observe. Now, a length k path, for example, here it is a length 3 path. In a tree has k plus 1 nodes in it. For example, here length is 3 and 4 nodes are there. In general, if there are k edges on the path, k plus 1 nodes must be there, which is also a non-result about graphs. Now, the length of the yield or a string derived of a parse tree of height h, which is generated by grammar in Chomsky normal form, is upper bounded by 2 to the power h minus 1. Why? Recall that the string derived is a string of terminals and only leaf nodes can hold terminal labels. So, the maximum length of the string is defined by the maximum number of leaf nodes, and here we said if the height is h, the maximum number of leaf nodes is 2 to the power h, then why is it that 1 less than h the power? Why is it not 2 to the power h? Because you know that it is a Cn of grammar, and if you are having a production with the RHS is a terminal, then it can contain only one terminal. So, at the last level you should replace a variable with a terminal, and where you will not get two child nodes, you will get only one. So, at the last level or at the second last level, the number of children each node is going to get is actually one, only one child. So, it is same as the height is h minus 1 because of this fact. I hope you are getting me, and this is basically because of this structure of a production in a Chomsky normal form grammar. If you are having two child nodes, that means you have not derived a terminal simple. If you derive a terminal simple, the last step will give you only one child rather than two childs, and that is why this is true, and this is a crucial fact about binary trees which we will be utilizing for deriving the pumping lemma for context free languages. So, the height of a derivation tree of a Chomsky normal form grammar for a terminal string of length 2 to the power n minus 1 will be at least n, not that. If the length is 2 to the power h minus 1, then the height must be h. So, if the length is 2 to the power n minus 1, the height must be at least n. So, that is a fact. So, if you are going for a height n parse tree, then the maximum length of the string derived is 2 to the power n minus 1. Please try to remember it. If the height is n, then the maximum length of the string derived can be 2 to the power n minus 1. With this we are moving forward, and we can have the basis for pumping lemma. Consider a context free grammar in Chomsky normal form with n number of n number of variables in it. Variables are also called non-terminals or capital letters. Suppose there are n. Let z be a string in the language such that the length of z is greater than or equal to 2 to the power n. What is n? The number of non-terminals or variables. Now, from the previous result we know that then the height of the tree must be at least n plus 1. If the height of the tree is n plus 1, then the length of the maximal string is 2 to the power n, 1 less than n is the power. This is exactly what we saw in the previous slide. Okay. So, if you are looking at a string whose length is greater than or equal to 2 to the power n, where n is the number of non-terminals, then the height of that parse tree must be at least n plus 1. Now, look at a path, longest path with height or length n plus 1, and from the previous slide then we know that if the number of edges is n plus 1, there are n plus 2 nodes. Okay, and out of the n plus 2 nodes, the last one is labeled with a terminal and all other nodes are labeled with non-terminals or variables. That is why you are able to expand. So, the last one has a terminal label and all other nodes here, n plus 1 nodes, have variables or non-terminals as label. Okay. Therefore, you are guaranteed to get a repeated non-terminal or a variable. Why? Because you have only n number of variables in the grammar, and on this path there are n plus 1 non-terminals appearing, that is at least one is repeated, that is guaranteed. And let x be the first repeated non-terminal from the leaf. You start from here, move up, you are guaranteed to get at least one non-terminal repeated. You find the first one repeated from here. So, you are finding some non-terminal x which is repeated, and let x be the first terminal repeated from the leaf node when you traverse up in the tree. Now, you can see that the yield can be subdivided into 5 substrings u, which is derived in the left part of this tree. Then if you look at this part, you call it as v, w, x and y. I will give you an example. Here is the binary tree that we have looked at for the example grammar, and this is the path that we are looking at, and capital S is the first repeated non-terminal if you move up. And now what are u, v, w, x and y? You can see it here. U is small a here, v, that is this part is small a, and w is ab, x is b, and y is again small b. Okay, that is not difficult to verify. Now you do cutting and pasting. Suppose you copy this tree and cut this large tree rooted at x and paste it over here. What you will get? So you will not get v and x. So that is what is going to happen. So remember, what we are doing is, we know that you can replace the tree rooted at x with another tree rooted at x. So we are going to take this subtree to this place, so you are getting this. So what is the yield now? U, w, y. This is one thing, or you can represent it as u followed by x, sorry, v 0 times, that v is not there, w followed by x, that x is not there now, 0 times, and y. So this was the original tree, and what we did in the previous case is we cut this tree and pasted this tree over there. You can do the other direction also. What you can do is, you can cut away this tree rooted at x and you can paste this bigger tree over here. So what you will get? You will get this. So what is the yield now? U, v square, w, x square, y. That is what you are getting. Here is the corresponding example, you can verify it. Now what we are observing is that, if you are looking at such a case where the length of the string derived is at least 2 to the power n, where n is the number of variables in the grammar, then you can see that for all I natural numbers, u v raised to I, w x raised to I, y is in the language, is the plumbing lemma. Now we can state it. For every context free language L, there exists a constant k such that for any string z in the language with the length of z greater than or equal to k, you can subdivide that string into u, v, w, x, y such that z is the concatenation of these strings, and if you concatenate v and x, it cannot be the null string, and if you look at the length of v, w, x, it must be less than or equal to k, and finally for all I, u v raised to I, w x raised to I, y must be in the language. Why is it so? You take k as any value greater than or equal to 2 to the power number of vertices. Then from the previous result we know that there is a repeated variable guaranteed, and then you can subdivide this like u v w x y. So, this is true. Then why is it that v x cannot be the empty string? Because you are considering a grammar in Chomsky normal form, the RHS cannot be epsilon. So, you cannot derive epsilon in any part of the tree. And why is it that this is true? Because we took x as the first repeated non-terminal from the leaf. So, till here x is the first repeated non-terminal. So, the maximum length of the path is n plus 1, and therefore, the maximum length of the string VWX is 2 to the power n, which is nothing but k. So, this follows. So, this is pumping lemma for context free languages. I hope you followed it. Otherwise, please watch it again. For the interest of time, we have to wind up. In the next class, we can see an application for pumping lemma, which is to prove that certain languages are non-context free. Thank you.